Hello, everyone. My name is Sun-Ho Kim, and I'm excited to present our paper, Insight Bench, towards grounded in situ guidance for robotic manipulation. Recently, VLA models have demonstrated remarkable capabilities in following natural language instructions. However, in our daily lives, we do not rely solely on verbal instructions. Instead, we constantly refer to various forms of in situ guidance embedded directly on objects. For instance, a push-pull sign on a door indicates not only its directional articulation feasibility, but also serves as a safety protocol between users. Similarly, markings on containers or boxes guide us on how to open them more effortlessly, while child-proof bottles provide specific mechanisms to unlock safety features. Furthermore, labels on remote controls or electronic buttons intuitively communicate the precise functional outcomes of each action. This raises a fundamental question. Can current VLA models truly comprehend and execute actions based on such visual-only in situ guidance? We argue that this ability to comprehend visual cues is indispensable for robots to operate autonomously in complex human-centric environments. While existing manipulation benchmarks like Libero, Maniskill, or Robocasa have significantly advanced the field, they all evaluate an agent's ability to follow commands external to the task environment. In contrast, in situ guide grounding is fundamentally different. These markings are co-located with the object and tightly coupled to specific, localized physical affordances. To bridge this gap, we introduce Insight Bench, a novel benchmark specifically designed to evaluate whether robotic systems can effectively understand in situ guidance and translate it into successful execution. Our work was conducted utilizing NVIDIA's Isaac Lab, and right figure shows base scene with Franca Panda robot arm. To systematically analyze this problem, we propose a comprehensive taxonomy comprising 5 distinct categories of in situ guidance. First, we have contact affordance. This simply tells the robot which specific component it needs to interact with. Next is action directional information. This restricts the robot's motion space to keep the actions valid, like following a rotational arrow on a cap. Then there's procedural guidance, which specifies the exact step-by-step sequence required for multi-step operations. We also look at in-part contact specification. This goes a bit deeper by detailing the precise manner or orientation of contact on a specific part. And finally, target disambiguation. This resolves ambiguity when a robot is faced with multiple identical candidate parts, like choosing the single correct drawer among many. We provide 4 types of tasks, which feature combinations of diverse objects in various guides: cabinet, door, bottle standard, and bottle squeeze. Each task isolates specific information types to test the agent's comprehension capabilities, and bottom table shows tasks to guide category mapping. To overcome data scarcity, our benchmark includes an automated procedure for generating data following the flow described below. First, guide to physics grounding ensures a strict programmatic coupling where the physical constraint is dynamically activated to align with the visual guide's semantics. After sample the tasks, objects, and guides, we generate constraints suitable for the selected guide and object. So how did we actually generate our large-scale action dataset? We developed an automated skill-based demo generation framework. Here is how it works. For scene generation, the system uses the object's 3D part information to sample the visual guide's position and orientation. This spatial randomization is then layered with standard domain randomizations to synthesize a diverse task scene. Next, the framework extracts the object's 3D state to sample low-level skill parameters. These are fed into our predefined skill sequences and executed via the QRobo motion planner to generate clean actions. Finally, if these actions successfully satisfy the programmatic success criteria, the trajectory is automatically curated and saved directly in the Lirobot format at 10 Hz. Through this pipeline, we produced over 14,000 demonstration trajectories, encompassing 783 distinct guide condition scenarios. Below is an example of our Insight dataset stored in the Lirobot format. To evaluate how effectively modern VLAs can leverage in situ guides, we benchmarked 3 baseline models across 3 distinct training conditions. First, NGVLA serves as our baseline, trained on a guideless dataset to measure inherent model biases. Second, GVLA is trained on the guided dataset, but it receives only a generic language command like open the door. This setting requires the agent to interpret the physical constraints purely from the visual cues on the object. Finally, LA-VLA is trained on the guided dataset, but receives explicit guide information within the text prompt, such as open the door, grasp the handle, rotate it clockwise, and then pull. Our overall results revealed that GVLA underperforms LI-VLA by a substantial margin. If today's VLA models were fully capable of grounding and utilizing visual guides, GVLA's performance should have approached that of LI-VLA. This stark contrast empirically demonstrates that current foundation models still suffer from a critical gap in visual-only grounding, failing to translate on-object semantics into physically constrained actions. For more details, including per-task success rates and comprehensive ablation studies, please refer to our full paper. Next, we showcase our real-world validation to confirm that the challenges of grounding in situ guides persist in reality. To bridge the sim-to-real gap efficiently, we took our simulation pre-trained GROUT policy and fine-tuned it using LoRa on a highly limited physical dataset, collecting just 15 real-world trajectories per task variation. We then evaluated the robot on the cabinet and bottle tasks across 10 trials per setting. As you can see in the graph, the real-world experiments yielded consistent trends with our simulation results. We hope InsightBench will drive future research toward robots that can truly interpret the visual cues in our everyday environments. Thank you so much for your time.